Okay guys, I want to make a quick video on how to deal with conservation of energy or work when you have a force versus displacement or force versus distance graph. The work equation is used when you can assume that the force that they give you does not change. Technically, it's the average force. But it also assumes it's a constant force. So when you get a problem, like I think you might see one on A53, maybe one on A52 or 51, where they give you a force versus distance graph, this force is not constant. A graph that would be representing a constant force would be a graph that just look like that. It does not change its value. So if you did force versus distance, you're just doing this equation here because this number doesn't change, this value. When you get something like this, okay, that's a little different. You can't use this. Okay, that's essentially no, cannot use that. So in problems like this, it seems like there's a big disconnect in terms of, well, how is this part of conservation of energy? It is in this way. If you look at something like, we have to have a way to make a graph like this. So this could be, say, the force produced by a rocket engine. You could look at this as the force produced when you use a bow and arrow. So if you have the bow and you're pulling the drawstring back before you fire the arrow, you've put work into pulling that bow back. And that can be represented by this graph here. As you pull it back, the force is going to go up. It's a non-constant force. With a rocket engine, that's a non-constant force. But both of these are potential energy, or examples of potential energy. Now, it's not gravitational potential energy, which is the potential energy based on something's height above the ground. You can have other aspects of potential energy, and briefly before we were all isolated here, I talked about elastic potential energy. Which is the energy possessed by a spring or a bow and arrow. We didn't get to into equations because we don't need them, but another one that happens a lot is chemical potential energy, and that's where we get into the rocket engine stuff. Okay, that is the energy produced or possessed by the fuel, and as it burns, that chemical energy turns into, or if you're lifting the rocket straight up, it's going to turn into kinetic energy and gravitational potential. So when you see this graph, this is actually, it's the work, it's the work of the energy possessed when you start the problem. It should be viewed as the potential energy of the object, but not gravitational. So this is going to be the starting energy when you look at a problem like a rocket engine or a bowstring. That's how you're going to look at this. This gets handed off into conservation of energy because you're going to release this energy or let it transform from a potential state into other forms. It could be kinetic, it could be gravitational potential. And so what I want to do is I'm going to set up a quick example to show you how you'd look at this. And then after this lecture here, think about going back and reviewing A53. It's problem 4 and 5, which looks kind of like that. So let me take a pause for a second, and I'm going to set up a little example problem. So say we had this graph again. Okay, and I'm going to use the same graph that they had in the problem, in that by the time this rocket has traveled 100 meters up, the engine force is 40,000 newtons. So this is a force versus displacement graph. So if I wanted to say the work done by the engine, okay, that equals the energy possessed. And if we remember about work done on this graph, it's the area. So if we want to know the initial stored energy, the PE initial, it's going to be 1/2 base times height. We're 100 meters long, and the height is 40,000 newtons. It's 1/2, so this is going to come out to be, this is going to be equal to 2 million joules of energy that the rocket engines are releasing, or that are stored in the engines, and they're going to be used to make the rocket go higher and make it go faster. So this is kind of a chart of what's happening here. And if I just reduce this down and basically say something like, we just dive right in and I say, how fast is the rocket traveling at 100 meters up? Think about what it's asking you. How fast is V? 100 meters up, that's your H. Okay. This is conservation of energy. It's asking you for a velocity connecting with a height and energy. So if you look at the big conservation of energy equation, if I kind of start out with just the general form, it's the kinetic energy plus the potential. Now what's going to happen, guys, is there's going to be two types of potential I got to look at here. So I'm going to kind of keep that in the back of my mind. That's going to equal, or it could possibly have kinetic and potential over here as well. And then I can have the energy loss term. But unless I tell you anything with friction being present, that's gone. Well, if we start and the rocket is on the launch pad, and we're asking, when it gets to here, what's its velocity? That's absolutely potential kinetic energy. But consider, this is where we're starting, and this is where we're ending. So take a look at this. The initial height of the rocket off the ground is 0. The initial velocity is 0, because you know what? It's not moving. And that would make you think that, well, everything's 0 over here, right? Well, no. Because there are two possible types of potential energy that can be going on here. There's gravitational potential, and there's, potential energy from the fuel. I just want to distinguish it from gravitational. You're absolutely right. If we look at this and we say it's not moving initially, and it has no height above the ground, then those are 0. Well, we can't have 0 on the left-hand side because nothing's going to move. There's another potential energy. This is like the work aspect on it, but this is what you have stored energy in the rocket engines. That is another type of potential. So you actually do have a value over here on the left-hand side. You have 2 million joules of energy in the bank before you start to spend it. Now you're going to spend it by raising it up off the ground, and then whatever you have left over is going to go into making it go faster. So we're going to look at this and say, well, the kinetic energy I know is 1/2. Now I didn't give you the mass of the rocket, so I got to kind of do that too. So I think when in the book they're using 500 kg. So I'm going to put that in here, 500, and then we want to figure out how fast it's going, so I'm going to have to go up to VF squared there. Now the potential energy is mgh. So 500, 10, 100. Now watch what happens. This is 2 million joules over here. My double quotes there means repeating the same value again. This is 250 times the final velocity squared. Now this is 500,000, 500,000. So think about this, guys. The amount of energy you start with is equal to the amount of energy you end with if friction is not present and air resistance is not present. So of the 2 million, we've burned up 500,000 of it just raising it off the ground at a constant velocity. So that means that we're playing around with 1,500,000 joules left by the time we get to that height. So this is what we have left to make it go fast. So at this point, this will tell us at that point how fast this rocket should be moving. So if I take this, and I'm going to kind of have to boost it over here because I'm running out of space. If you do 1,500,000 divided by 250, and then remember to take the square root, That's going to give you your final velocity. So I did a couple steps in there. With the VF, when you're solving for the final velocity like this, it's always like, divide by that term, square root it, and that's going to give you that number. I think this comes out to be around 78 and something meters per second. But this is kind of a fast way to look at this. I know in the problem they actually I call it baby stepping you through, where they'll say, hey, what's the potential energy at this point? Hey, what's the kinetic energy at this point? I'm just diving in and saying, listen, you got this amount of initial energy you start with. We have to break it up into, of the 2 million, we've used 500,000 to get it to here, which means we have 1.5 million left. Well, that 1.5 million, how fast can that make an object go if you have to move 500 kilograms worth of inertia there? And that'll give you the final velocity of that object. That's how you would look at using a force distance graph to work through a conservation of energy problem. It's your starting energy in the problem, basically. I want to say, quote, it's your left-hand side, and then you start to work on the right-hand side after that. So I hope that clears a few things up for you. All right? Thanks, guys.